Good day and welcome back everyone. And We are continuing our exploration on unit number 3, Advanced Drone Operation and Control System, which is arguably one of the most crucial and exciting part of our entire course. In our last session, we laid the complete theoretical groundwork of understanding how MAV or micro air vehicle operates. We begin by looking at the high-level system architecture, breaking the drone down into core hardware and software components. From here, we dwell into the essential mathematics, establishing the importance of coordinate frame and discussing how we use Euler's angle to represent the drone altitude. We then move on from representation of motion, first by defining the kinematics of MAV, the 12th state that describes its position, velocity, orientation, and angular rates. With that foundation, we progress to dynamic, applying Newton's second law to both translation and of rotation motion to understand the force and moment that causes the drone to move. We specifically model the primary forces involved: the constant pull of the gravity, the controllable force of propulsion from the motor, and the complex aerodynamic force of lift and drag that arises from the drone's interaction with the air. We conclude by discussing how aerodynamic movement are generated either by controlled surface on fixed wing MAV or by differential thrust on multirotor to control the aircraft's altitude. Today, we are going to build directly upon that theoretical foundation and bring it into the real world. A perfect mathematical model is one thing, but a real MAV must operate in dynamic and unpredictable environment, and it must rely on imperfect physical sensor to understand its own state and its surrounding. So, in this lecture, we will translate from the ideal model to the practical application. We will begin by analyzing the significant effect of wind and atmospheric disturbance on flight performance. Then we will spend a considerable amount of time on the drone's sensor system, taking a detailed look at the suite of onboard sensors like accelerometer, gyros, pressure sensor, magnetometer, and GPS, which serves as the MAV's eyes and ears. We will examine the principle behind how each of these sensors work, what they measure, and just as importantly, their limitation and source of error. Finally, we will tackle on one of the most crucial topics in the modern robotics, the state estimation. This is a process of taking noisy, incomplete data from multiple sensors and fuse it together to create a single, accurate, and reliably estimate of drone's true state. This is the brain power that allows the MAV to function reliably even when the individual sensors are imperfect. By the end of our session today, we will have a much clearer picture of how drone truly perceives this world and navigates through it. Perceive this world and navigate through it. As we begin to bridge the gap between our theoretical model and the real world performance, the first and the most persisting environmental factor we must account for this wind is wind. MAV operates in dynamic atmospheric conditions where the wind significantly impacts the flight performance. As an autopilot that doesn't understand a compensation for wind will be unable to navigate accurately. To properly handle this, we must distinguish velocity. There are three key velocity we need to define. First, ground speed, VG, which is the MAV's velocity relative to the ground. This is what matters for the mission. It is how the drone is actually moving across the landscape. The second is the airspeed, VE, the MAV's velocity relative to air mass. This is the speed that the drone's aerodynamic surface feels, and it is what determines lift and drag. The third is the wind speed, which is the velocity of the air mass relative to the ground. These three velocity are linked by the wind's triangle relationship, which is simply vector addition. Vg is equal to Va plus Vw. The diagram of the wind triangle on the slide illustrates this perfectly. An aircraft wants to travel along a 90 course and 110 course ground speed. However, there is a strong wind blowing. In order to counteract this wind and maintain the desired path, the pilot cannot simply point the aircraft nose at 90 degrees. Instead, they must fly at 80-degree heading and 120 knot speed, pointing the aircraft into the wind. The angle between the aircraft's heading and its actual course over the ground is the drift angle, and in this case it requires 8-degree left correction. The MEV pilot must perform this same calculation continuously to stay on the planned flight path. To ensure our control system and robust enough for these conditions, we must also simulate them. These atmospheric disturbances are modeled as constant wind field plus turbulence using dry, uh, uh, dry, Dryden model for realistic simulation. This allows us to test our navigation and control algorithm in a virtual environment that includes not only steady wind but also the random gust and turbulence that the MEV will encounter in the real world. To navigate the real world and compensate for factors like wind, a drone need to be able to sense its motion and its surrounding. This brings us to the topic of onboard sensor that makes this possible. As the slide states, the modern MAV rely on a suite of lightweight sensor to achieve autonomous flight capacities. The ability of a drone to fly with such stability and intelligence is not magic. It is a direct result of incredible sensor technology packed into their tiny airframes. The critical enabler behind this revolution are small, lightweight, and solid-state sensor using MEMS, micro electrical mechanical system technologies. MEMS are incredibly small devices that combines mechanical and electrical components on single silicon chip, much like a computer processor. This technology allows us to create sensors like the one picture on the slide, which are not only tiny and lightweight, but also power efficient and highly resistant to vibration. This is a miniaturization that truly enables MAV's autonomy, as it allows us to build sophisticated sensing system without adding prohibited weight or cost to the aircraft. A typical sensor suits on the MAV includes several components, each with a specific job. First, we have accelerometers, which measures specific force. These sensors are crucial for determining the orientation of the drone relative to the gravity. The next are the gyros, which measures the angular velocity. This is the data that tells the autopilot how fast the drone is rolling, pitching, and yawing, and it is absolutely essential for flight stability loop that keeps the drone in level. We also use pressure sensor to determine the altitude and airspeed. A barometric measurement which measures the air pressure to calculate the drone's height, while the pilot tube system can measure the dynamic pressure to find its speed through the air. To know which direction it is heading, the MAV uses magnetometer, which provides heading information by acting as a digital compass. Finally, to know this absolute location on the globe, the drone relies on GPS, which provides global positioning data. The ultimate purpose of gathering all this information is fed to the drone's brain. As the slide notes, these sensors provide essential data for guidance, navigation, and control system. The GNC system is the heart of the drone's autonomy. The navigation component uses the sensor data to figure out where the drone is and how it is oriented. The guidance component uses this information to determine the best path to waypoint or to accomplish the mission objective. And the control component takes the command from the guidance system and translate them into the precise motor action needed to fly the drone along the path. Every sensor in this suite plays an indispensable role in making this complex process possible. Now, let's begin our deep dive into the sensor suite by focusing on the first and one of the most important sensor on any MAVs, the accelerometer. The title of the slide is accelerometer, measuring specific force. These fundamental sensors that measure the specific force through proof mass displacement. To understand how they work, we look at their underlying principle of operation. As the diagram illustrates, an accelerometer can be a conceptual model as the proof mass suspended by a spring. When the sensor casing accelerate, the internal mass due to its inertia tend to lag behind. This moment displaces the mass the proportion to accelerate. This tiny displacement is then measured electronically, often by detecting a change in capacitance between the moving mass and the fixed plate. This electronic signal is then converted into a measurement of acceleration. A crucial point to understand is what an accelerometer actually measures. It does not measure the total acceleration of the aircraft, relative to the ground. Instead, accelerometer measure specific force F. The specific force is the difference between ac- aircraft acceleration A and a gravitational acceleration G, which can be expressed by the equation F equal to A minus T. This critical this is a critical uh, distinction. For example, if a drone is sitting perfectly still on the ground, its aircraft acceleration A is zero. However, the accelerometer will not read zero. The gravity is pulling its spoof mass down, and the sensor measures the equal and opposite force from the internal spring folding up. Therefore, it will report an upward acceleration of 1 g. Conversely, if the drone were in free fall, both casing and proof mass would be accelerating downward at the same rate due to gravity. There would be no displacement, and the accelerometer would read zero. So specific force is non-gravitational force per unit mass if the acceleration that would be physically that you would feel free. Because of this physical principle, the real world output of an accelerometer is quite complex, which is why we need a detailed mathematical model to interpret its reading. The sensor's output include linear acceleration, Coriolis acceleration, gravitational acceleration, and noise component. The linear acceleration is typically the value we are trying to determine, but we have to account for other terms also. Coriolis acceleration terms appear because the sensor is on rotating body. The gravitational term, as we discussed, is always present and is actually used for determining the drone's altitude relative downward. And finally, like any physical sensor, the output always includes random noise component that must be filtered out. Understanding this complex output is the first step towards using accelerometer data effectively in a navigation system. Continuing our content of MAV sensor system, we now turn to the rotational equivalency of accelerometer, the rate gyro. Rate gyros are essential for measuring rotational motion in MAVs, providing critical data for stabilization and control. If the acceleration tells the MAV which way is down, the rate gyro tells it how fast it spins. This high-speed feedback is absolute core of the autopilot ability to keep the aircraft stable, as it allows the system to instantly counteract any unwanted rotation caused by wind, gust, or other disturbances. While the diagram on this slide shows a classic mechanical gyroscope with a large spinning wheel, the operational principle of sensor in modern MAV is quite different and much more compact. The modern MEMS gyros use vibration spoof mass that experience Coriolis acceleration when subjected to angular motion. Inside the tiny MEMS chip, a microscopic mass is driven to vibrate back and forth at high frequency. When the drone rotates, the Coriolis effect exerts a force on this vibrating mass pushing it in a direction perpendicular to its vibration. The sensor measures this way, this sideway displacement electronically, and the magnitude of that displacement is directly proportional to the rate of rotation. This clever design allows for the measurement of angular velocity, which no large, no larger a power-hungry spinning bar, making it perfect for small, lightweight MAVs. The specific measurement provided by this sensor are the drone's angular rate about its own body axis. This provides angular rates P, Q, R about the body axis. These three values correspond directly to the rotational velocity we defined in our kinematic model. Specifically, P is the roll axis, Q is the pitch rate along y-axis, and R is the yaw rate along z-axis. The flight control continuously monitors these three numbers, and if it detects non-zero value that wasn't commanded for the instant a roll comes by wind, it will immediately adjust the motor speed to create a counteract torque and drive that rate back to zero. However, like all real-world sensors, the rate gyro has their challenges. Its most significantly issue is that they are susceptible to bias drift. An ideal gyros could output a specific or perfect zero when stationary, but a real gyro has a small non-zero output called as a bias. This bias is not constant. It drifts slowly over time and is often temperature dependent. If we were to calculate the drone's angle by simply integrating these rate measurements, this small drifting error would accumulate, leading to a large and even an increasing error in our altitude estimate. This is why the gyro requires careful calibration and periodic zeroing for accurate measurement. This is also the primary motivation for sensor fusion. When we combine the fast but drifty measurement from the gyros with a slow but stable orientation data from an accelerometer to get the to get the best of both the worlds. Our sensor overview now brings us to the class of sensor that measure property of the atmosphere itself, pressure sensor. These devices are not for measuring the force or rotation, but instead provides critical altitude and airspeed for MAV navigation and control system. Knowing the MAV's height and its speed relative to the air are fundamental requirements for safe and efficient flight. There are two primary types of pressure sensor used on MAV to accomplish this. The first is the absolute pressure sensor, which functions as the barometer or altimeter. This sensor simply measures the ambient atmospheric pressure. It is well-known principle that the atmospheric pressure decreases with altitude in a predictable way. The sensor leverages this relationship and is used to determine the height above the ground level, also known as HAGL, through the parametric formula. By measuring the local air pressure, the MAV autopilot can calculate its current altitude. This barometric altitude is often more stable and responsive to vertical changes that GPS altitude makes it a critical input for tasks like terrain following and maintaining a constant height. Uh, the second type is the differential pressure sensor, which is most commonly implemented as pilot static system or pilot tube. This sensor is not measuring altitude but for determining airspeed. It measures dynamic pressure by comparing static and total pressure. As the diagram shows, the tube opening faces directly into the airflow to measure the total pressure, which is combined of the static ambient pressure and the dynamic pressure from the air's motion. A separate static port measures only the static pressure. The difference between these two readings gives you the dynamic pressure. This sensor is then used to calculate airspeed (VA) using Bernoulli's principle. The specific formula is VA is equal to 2Q divided by rho, where Q is the dynamic pressure and P is the air density. Measuring airspeed directly is vital, especially for fixed-wing MAVs, as it is the speed of air over the wings that generates lift, not the speed of aircraft over the ground. As with the other sensor we discussed, pressure sensors have their own source of error that we must account for in our model. This measurement are characterized by bias drift and Gaussian noise. The sensor bias can drift with change in temperature, and its output will always contain a degree of random noise. For this reason, the sensor are requires calibration and filtering for accurate measurement. The raw pressure reading must be processed by the autopilot to remove noise and correct for bias before they can be reliably used by the guidance system, the navigation system, and the control system. This again highlights the importance of state estimation algorithm that we will cover shortly. To complete its understanding of this state, a MAV need a sensor of direction. This provided by direct compass, more formally known as the magnetometer. As the title suggests, their job is to provide a magnetic heading. These sensors detect Earth's magnetic field to provide heading information, which is essentially for the MAV's navigation. While GPS can tell a drone where it is, the magnetometer tells it is which way facing, allowing it to orient itself for a flight for the next waypoint. The underlying principle of magnetometer is quite straightforward. It utilizes Earth's three-dimensional magnetic field as a reference for for determining orientation relative to the magnetic north. The Earth itself generates a massive, uh, albeit weak magnetic field, and the sensor on the MAV is sensitive enough to detect it. By measuring the direction of local magnetic fields, the MAV can reliably determine its heading. The measurement process is handled by three-axis magnetometer aligned with the body axis. These sensors provide magnetic field strength measurement in all directions, which are used to calculate magnetic heading. However, using this using this measurement for navigation is not as simple as just pointing towards magnetic north. A significant complaint is that magnetic north varies with location, requiring compensation model like the World Magnetic Model (WMM) to convert between magnetic and true north. The direction of the magnetic North Pole is not the same as the direction of the geographical North Pole, and the difference between them, known as declination changes depends on where you are on the globe. Therefore, the MAV navigation software must use its current GPS position to look up the local declination from a model like WMM and apply a correction to get an accurate true north heading. Perhaps the biggest operational difficulty with magnetometer involves their challenge because the Earth's magnetic field is so weak. These sensors are highly susceptible to uh, interference from nearby ferromagnetic material and electronic system. The steel screw in the drone's own frame, more significantly the strongest magnetic field generated by the current flow to the motor, can easily overwhelm the terrestrial field and give a false reading. This vulnerability is requiring a careful calibration and mounting. To mitigate this, the magnetometer are often mounted on masts as far from the power lines and motors as possible. Additionally, a rigorous calibration process is necessary where MAV is slowly rotated through all possible orientation to allow the software to build a map of drone's own magnetic field and learn to subtract it from the measurement. While the sensor we discussed so far are excellent at determining the MAV's orientation and its motion relative to the air, they can tell the drone where it is on the surface of the Earth. For that, we rely on the Global Positioning System or GPS. GPS technology provides absolute position information, making it critical enabling technology for small UAVs. It is significant to modern drone operation cannot be overstated. GPS is what enables autonomous navigation, waypoint following, and return to home capability that fundamentals to MAV operation. This ability to create flight plan on map and have the drone execute it is a direct result of having reliable GPS receiver on board. The core principle behind GPS is the process called positional triangulation, an constellation of satellite orbiting the Earth is constantly broadcasting precise timing signal. The GPS receiver is in the MAV listen for these signal and measure the time it makes for them to arrive. By knowing the time, it can calculate its distance or a pseudo-orange from each satellite. The system requires at least 4 satellite pseudo-orange measurements to resolve this. Its full state. 3 of these measurements are used to triangulate the receiver's 3D position, latitude, longitude, and altitude. The force measurement is needed to resolve for a critical variable, the receiver's clock offset. The timing requirement for GPS are so extreme that a small inaccuracy in the receiver's inexpensive quartz clock would lead to enormous precision error. The fourth satellite signal allows the receiver to constantly correct its own clock against the highly accurate atomic clock in the satellite, thus ensuring a precise positional lock. Of course, this process is not perfect, and there is a several source of measurement error. The total error budget is often referred to as the user equivalent range error or UERE, and it is the source included several factors. The first are the MRS data error, which includes which there are inaccurate in the satellite's reported position. The second are the satellite's receiver clock error. Despite the correction, a tiny residual timing error can be removed. Perhaps the most significant source of error are standard errors, which are ionospheric or uh, tropospheric delays. As the satellite radio signal travels through the Earth's atmosphere, it bends and slows down, which makes the calculation distance appear longer than it actually is. Advanced GPS system uses dual frequency receiver and augmentation system to model and correct for these errors. But for a typical MAV, it is important to understand that these environmental factors will always introduce some degree of uncertainty into the positional measurement. Beyond the inherent error source we just discussed, the accuracy of GPS measurement is highly dependent on several operational factors. As the slide indicates, GPS provide both positional and velocity data with accurate independent on satellite geometry and signal quality. A primary factor affecting accuracy is the concept known as dilution of precision or DOP. The geometric configuration of a satellite affects position accuracy. As the diagram on the slide illustrates, when the satellite, the receiver, is tracking all are clustered together in the sky, it results in a poor geometry or a high DOP value. This configuration, any small error in the timing measurement gets magnified or diluted into a large error in the calculated position. Conversely, when the satellite is spread wide across the sky, the geometry is strong, resulting in low TOP value and much more accurate positional fix. This geometrical error is broken down into several components, including HDOP, horizontal dilution of precision, and VDOP, vertical dilution of precision. For any pilot or autonomous system, the key takeaway is the lower DOP value indicates better accuracy. When we model the output of the GPS receiver for our control system, we need to understand the nature of the data it provides. The position model for typical GPS unit is discretizing time output, which is noise and slowly varying bias. This means It delivers positional update in distant packets, not as a continuous stream, and they up, and these updates are typically updated at 1 to 10 Hz. This is relatively slow update rate compared to the initial sensor, and the data is never perfectly clean. In addition to position, GPS also provide an excellent velocity measurement. Instead of simply calculating velocity by taking the difference between 2 points, modern receivers use a much elegant method. The velocity measurement are derived from the Doppler shift of the satellite signal. As the MAV move, the frequency of the carrier wave from the satellite appears to change, and by measuring this change, the receiver can calculate this velocity very precisely. This carrier phase Doppler provides accurate ground speed, VG, and course X measurement. In this fact, these velocity readings are often more reliable than differential position data. Attempting to calculate velocity by subtracting two noisy position uh, measurement would result in an even noisier and very unreliable velocity estimate. The Doppler method, by contrast, gives a smooth and accurate reading of the MAV's speed and direction over the ground. While GPS have been revolutionary tool for MAVs, it has its limitation. It can be blocked by buildings, jammed by interference, or may simply be unavailable indoor. This is why the next frontier in the drone autonomy is the ground guidance navigation. This is a key capacity that provides MAV with the ability to perceive and interact with the environment without relying solely on the GPS. By using camera as primary sensor, a drone can navigate much like a human or an animal does. The motivation for this approach is twofold. First, the technology is accessible and effective. Electro-optical infrared (IE EOIR) cameras offer an inexpensive platform for environmental sensing. These are small, lightweight, consumer light power and provides an incredibly rich stream of data about the world. Second, this approach is inspired by biological vision system in nature. Insect, birds, and other animals perform incredible feats on navigation and acrobatic flight using vision, giving us a powerful blueprint to learn from. The diagram on the slide shows how camera can provide a current view that feeds into a sophisticated mission algorithm and enabling intelligence and safety actions. However, using vision introduces new layers of complexity, particularly when it comes to geometry. To make sense of an image, multiple reference frames must be managed. This includes fixed inertial frame, the drone's own body frame, the gimbal frame if the camera is mounted on a stabilized platform, and finally the camera frame itself, which is relative to the camera sensor. The drone's navigation system must be enabled to instantly and accurately transform coordinate between all these frames to understand where An object seen in 2D image is actually positioned or located in the 3D space. The mathematics that governs this process falls under heading of projective geometry. This is the set of rules that maps 3D object to 2D projection on the image plane. A camera image is flat 2D representation of the 3D world, and projective geometry is what allows us to relate the two. This process is what defines the normalized line of straight vector, which is vector pointing from the camera center to a specific feature in the scene. This vector is essential for feature tracking and obstacle avoidance. By tracking how the line of sight vector to various feature changes as the MAV moves, the software can uh, uh, deduce its own motion through environment and build 3D map of its surrounding, allowing it to navigate precisely and avoid collision, all without using a single GPS signal. Over the last several slides, we have examined the suite of sensors that MAV uses to uh, perceive this world, from accelerometer and gyros to GPS and camera. The recurring theme that we have every sensor has limitation. It might be noisy, it might drift over time, or it might be susceptible to environmental interference. This brings us to the critical topic that ties everything together: the need for state estimate. The core reason this is so important is that state estimate is essential for MAVs because many critical flight parameters cannot directly measured by onboard sensor. We cannot simply take a sensor reading and trust it as the absolute truth. There are significant sensor limitations that we must overcome. In fact, many system states are not directly measured by the available sensor. For example, a drone has no sensor that directly measures its roll and pitch angle. Instead, we have to interpret these angles by processing and combining data from accelerometer and gyroscope. Similarly, there is no direct way to measure the position in GPS denial environment. We often need to estimate key velocity component and environmental factors like wind condition, as there is no simple lightweight sensor that can measure the wind velocity directly. The reason we must go to the trouble of the estimate these unmeasured state is that autopilot requires accurate state estimate for effective control, stability, and navigation. A control system is only as good as the information it acts upon. If the autopilot has inaccurate beliefs about its own altitude or position, its command to the motor will be wrong, which can lead to unstable flight or completely failure to navigate its destination. Providing clean, accurate, and reliable state information to the controller is perhaps the single most important job of the MEV's navigating software. The solution to this problem is process that involves filtering, and fusioning. This process combines noisy sensor measurement from multiple sources to interfere unmeasured state and improves accuracy to measure state. This is the elegant solution to our sensor limitation. We take the fast but drifty data from the rate gyros and fuse it with the slow but stable data from the accelerometer and magnetometer to produce an altitude estimate that is both fast and stable. We combine the high-speed data from our inertial sensor with the slow but absolute data absolute data from the GPS to get the position estimate that is accurate both in short term and the long term. This powerful technique of sensor fusion allows us to take a collection of imperfect sensor and create a single unified state estimate that is far more accurate and reliable than what a single sensor would be provide on its own. Having established the critical need for the state estimation, let's begin by exploring the most straightforward approach. This slide introduces simple state estimation, low-pass filtering, and inversion. These basic state estimate technique provides a foundation for most advanced method using simple filtering and sensor model inversions. These uh, they represent the first logical step in processing raw sensor data before feeding it into the controller. One of the most common application for this simple technique is in the cleaning up a measurement for angular weights. The value from rate gyros are directly estimated by low-pass filtering rate gyro signal to reduce noise while preserving the signal integrity. A low-pass filter is an algorithm that smooths out a signal by reducing high-frequency fluctuation, which are typically caused by sensors noise or vibration. The graph on the slide shows the frequency response of such filters, illustrating how it allows low-frequency signal to pass through while attending high-frequency noises. A common implementation is a simple weighted average, as shown in the equation of the slide, where A is the filter coefficient that determines the amount of smoothing. By applying this filter, we can get much cleaner estimate of the drone's true angular velocity. A similar approach is used for altitude and airspeed. These states are estimated by low-pass filtering pressure sensor output and inverting sensor model to convert the pressure to physical quantities. First, a low-pass filter is applied to the raw pressure reading to smooth out them. Then, a second step, model inversion, is required. The sensor gives us the measurement of pressure, but the autopilot needs to know the altitude in meter and airspeed in meter per second. This inversion process is simply applying of physical model like barometric formula or Bernoulli's formula to convert the clean pressure reading into useful physical unit that the physical control system can act upon. However, it is crucial to understand the limitation of this simple method. There are starting point, not a complete solution. These simple methods are ineffective for Euler's angle or position during accelerated flight. A simple filter cannot correct its inherent drift of gyroscope, so it cannot be used to accurately track altitude over long periods. Similarly, it cannot accurately estimate position by integrating acceleration, especially when the MAV is maneuvering. Furthermore, this simple technique doesn't account for system dynamic or sensor across couple sensor cross coupling. They treat each sensor in a vacuum with no knowledge of the underlying physics of aircraft. This is a major drawback and is the primary motivation for most advanced dynamic observer theories that we will discuss next. A simple filter we just looked at a very useful for basic noise reduction, but they fell short when dealing with more complex problems like sensor drift and estimating unmeasured state. To overcome these challenges, we must move beyond simple filter and into the realm of dynamic observer theory. Advanced state its estimation technique incorporates system dynamics and measurement model to achieve high accuracy and robustness. The key difference is that these advanced methods have knowledge of the MAV's physics. They don't just at the sensor signal, they look at as in the context of how the drone is expected to behave. The core of this approach is the observer's concept. An observer estimates state of a system by combining these essential pieces of information. First, it uses a mathematical model of the system's dynamics. It This is the predictive component. The observer takes the last known state and control input sent to the motor, and uses its internal physics model to predict what the new state would be. Second, it incorporates the actual sensor measurement. This is the measurement update step. Third, and the most importantly, it calculates correction terms based on the measuring errors. The observer compares this prediction with the actual sensor measurement. The difference between these two is the error, which is then used to correct the initial prediction. This constant cycle of predicting and correcting allows the observer to track the true state of the system with incredible accuracy, even when the sensor measurements are noisy and incomplete. In practice, this is often implemented as a continuous discrete observer. The observer propagates state estimates between sampling using new model. In the time between the sensor update, it is constantly running the physical model forward. It is then updates them when the measurement are received. This hybrid approach effectively accounts for both continuous dynamic and discrete measurement, which is perfectly matched for the physical system that moves continuously but is measured by digital sensor at discrete time interval. This observation theory is the Kalman filter foundation. It serves as the precursor for most advanced estimation technique like the extended Kalman filter (EKF) and uncentered Kalman filter (UKF). The Kalman filter is a specific optimal implementation of the observer's concept for linear system. The EKF and the UKF are powerful adaptations of this filter that can handle complex nonlinear dynamics of MAVs. These algorithms are widely used in MAV navigation system and represents the state of the art in fusion in sensor fusion. They are the engine that takes all of the disparate uh, uh, dis, dis, disparate noise sensor data we have discussed and combined it into a single coherent state estimate that is necessary for advanced drone operation.